All right then. I welcome everyone to AAC's knowledge sharing session on the hidden meaning of symmetry, talk by Abhishek Reddy, brought to you by the Physics SIG. In this talk, the speaker is going to discuss the physical meaning of symmetry and then give it a mathematical basis, and then continue the discussion into the real application of symmetry in physics. All right then. Here's Abhishek.
My name is Abhishek Reddy, third year BTech, mechanical engineering from NITK. So I think I'll start with why I wanted to talk about symmetry. So initially, I really didn't like the concept of symmetry. It didn't make sense to me, like why people look for symmetry in like the real world and stuff. But then once I saw the math behind it and even like the physical meaning of it, it just blew me away. So maybe it might blow you away, but if it doesn't, just whatever. Okay, so what is symmetry? Like I've tried to find out the meaning of symmetry, like the definition of symmetry, but there's no certain like definition of symmetry in like grammatical sense. But so it comes from a Greek word which translates to like proportions, beautiful, and stuff like that. But then in the general sense, when an object undergoes like a certain transformation, like around an axis or any rotational transformation, when it remains unchanged, we like consider it symmetric. And before anyone says anything, I know this butterfly is actually bilaterally symmetric, but then it's only a biological term when you consider something bilaterally symmetrical. And so we know that there are many forms of symmetry. So the simplest form would be a radial symmetry, where when you just consider one axis and just flip it, and it looks exactly the same. There's even reflection symmetry, which you can just basically looking in the mirror and you both look the same. Rotational symmetry also exists. I put a bindi instead of a snowflake because I don't know how many of you have actually seen a snowflake in your life. So, but I've cut many bindis in my life. So when you rotate this bindi like by 60 degrees or something, you get the exact same shape again. So this is an example of rotational symmetry, and then fidget spinner also, like every 190 degrees it should be the same. Or 90, yeah. This is one I just made up, approximate symmetry. Like we can just consider the Milky Way as approximately symmetric because it's just too much of a hassle to check if both sides are the same. Like if I just consider this as an axis, it's too much of a hassle to consider the amount of matter here, and see if it's the same. It's just easier to approximately consider it symmetric. So now this is all the stuff we see in nature and stuff, but this is not exactly what it means in mathematics, but it's somewhat related. So in physics or in math, which is basically the same, when so consider a mathematical function, for instance. If you change one parameter and the function doesn't change, it's considered symmetric under that change in parameter. So when a system like undergoes a certain transformation and it doesn't change, it's considered symmetric. So for example, maybe you can consider throwing a ball, just for example. So if I throw a ball now versus when I throw a ball, say 20 years from now, these three equations are still going to govern that law, like the motion of the ball. It doesn't matter, but when I throw it, it just matters that I throw it. So you can consider that as time symmetric. It doesn't depend, even if it transforms the time, it doesn't matter. It doesn't affect the ball's motion. So in physics, there are numerous types of symmetry, but then we just consider mainly four usually. Okay, you can just start off with global and local symmetry. So then maybe you can consider a moving car. So if you move on a straight road, maybe you can consider that symmetric along the road. But then when you consider the whole Earth as a thing, it's not symmetric at all. I hope you understood that. But then, so local symmetry may not be global symmetry, but then local symmetry has its own uses. Then there's discrete symmetry and continuous symmetry. These symmetries are the more of the basics of physics and stuff. Like, yeah, we get to why it's more like important for us. And gauge symmetry, this kind of symmetry is very important in particle physics. It determines each and every kind of force and their particle that they exhibit. Okay, so discrete symmetries. So then there are three types of discrete symmetries. One is charge conjugation, another one is parity, and another one is time reversals. So in charge conjugation, it states that for every particle there'll be an antiparticle with the opposite charge. And electromagnetic forces and gravitational forces are charge conjugation symmetry. Basically, if I take an atom first, for example, and I change the protons to positive charge, to a negative charge, and the electrons to positive charge, the physics of the system can be still be shown, like it can still be done, like worked out using our physics. And then parity symmetric. So then it's like mirror. So if there was a mirror image of a universe, it would be called a parity symmetry. So it's basically like a left-handedness or a right-handedness of an object. Like it's the spin of the object, it can be reversed. So it's not in only one dimension, like not x equal to minus x and stuff. It's the all three dimensions you have to reverse it. Like for parity symmetry, you can consider like maybe a clock facing a mirror. From your perspective, the clock is moving clockwise. But then when you look at the mirror, it's moving anti-clockwise. So then you can say that that system is not parity symmetric. And then there's time reversal. It's basically like if I move reverse in time, will the physics of the universe be the same? The thing is, no. If I just go backwards in time, the universe will not function the same as it were. Like our laws of physics will not govern that. So actually, all these three symmetric C symmetry, P symmetry, and T symmetry, all are individually broken at one point or the other by one force or the other. But when you put all of these together, you get CPT symmetry. This symmetry, like, it holds strong. Like, there's no, like, even if a universe was there, which had like, every charge in the universe was changed from positive to negative and negative to positive, and even it was the axes were flipped, which is parity, and it moved backwards in time instead of forward in time, which is T. It would our laws of physics would still govern the entire universe. There's no problem with that. So yeah, so then it's not actually it's rewind time. It's charge conjugation parity time reversal. Because when you just rewind, it just doesn't work. When you do all three at once, yeah, that's correct. So then there's another kind of symmetry known as continuous symmetry. So in continuous symmetry, it's like a function will continuously change. Okay, yeah. So it'll continue, like the function remains unchanged under continuous transformations. Then it is said to be continuously symmetric. So maybe you can consider something like just consider like the ISS, for example. If you at any point in time or any position, the laws of physics will govern what's going on, right? If you change the position from one point, like from one point in the orbit to even like the polar opposite, it's fine. The laws of physics will remain unchanged. So basically, under these two transformation, the system function or the system will remain absolutely the same. There's no issue. Uh, Another example of this would be like traveling in a car on a straight road. I'm going to be using this example quite a lot. So when you're traveling in a car at like any velocity or even acceleration, it doesn't. You have, even if you move from one point to another at any time, you can start during the day, you can start during the night. It doesn't matter. So maybe this is like a kind of space-time symmetry. This is like only one example of continuous symmetry. There are innumerous. Okay. So then like this is the main topic of the talk, I guess. Conservation laws. So I think everyone knows what a conservation law is, but in a mathematical sense, it's when like a quantity, a measurable quantity rather, remains unchanged under certain operations which are conducted on it, and the quantity is said to be conserved. So we all know that energy is conserved, momentum is conserved in like certain circumstances. But has anyone ever questioned why? It's like so hold true, like what true? Okay, so it's so embedded in our mind that law of energy is so true, and like why would it not be true? Like we've never questioned why it's true. Like if I ask anyone why do you think it's true, they'll probably tell me like a law of thermodynamics that states that you can't lose any energy, and thermodynamics is like absolute and stuff. That's true in a sense, but then there's always a hidden meaning behind everything. So like anytime you want to learn physics, there's always math holding you back. Like it's just the worst. So maybe I thought I'll just give you a little bit of mathematical background to just understand a bit of what I'm going to say later on in the talk. So I wanted to talk about Lagrangian mechanics. I hope I'm not going too fast. So this guy, Joseph Louis Lagrange, in like 1788, he published Lagrangian mechanics, but his works were based on some Arabic guy like almost 700 years back or more than that. So mechanics as a whole is used to describe the dynamics of a system, like the motion, what is going to happen when, why it happens and stuff. But yeah, so Newtonian mechanics we know is one kind of mechanics. There's Lagrangian mechanics, there's quantum mechanics. There's so many type of mechanics. So Lagrange is just one of many. Why it's important in a sense that it helps simplify problems which Newtonian mechanics just fails to do. Like, for example, maybe a double pendulum. Depending on the starting location, the end point can be wild. You just go nuts. Then Lagrangian mechanics helps you determine that. So Lagrangian mechanics is revolving around a quantity known as the Lagrangian. Like in Newtonian mechanics, we consider force as an object, right? Like I'm pretty sure in 11th and 12th and stuff, you'd always used to use forces to determine what would happen to an object. But here we use a quantity called the Lagrangian. He just named everything after himself. So then the Lagrangian of a system, describes the entire dynamics of a system. And like let's just not consider relativity for this talk. Like it's just too much, I guess. So for just a normal circumstance, we just use L equal to T minus V, where L is the Lagrangian and T is the kinetic energy of the system and V is the potential energy of the system. So like to really understand what how Lagrangian mechanics works, we have to consider the principle of least action. So in Newtonian mechanics, we just consider the force and then we see where that force takes us, right? But in Lagrangian mechanics, we have to find a different way. So I'm pretty sure everyone has heard about Fermat's principle where light will always take the path which takes the least amount of time. But yeah, but light and matter aren't the same thing, right? Light has no mass, matter has some mass or something. So what quantity should have been chosen for Lagrangian mechanics? So he's like, okay, I'm going to take the entire path of it, like the entire path. So consider this pendulum. So he just considered this entire path, and he asked, why does it take this path? And even like when an object moves from one point to another, why does it take a specified path and not just some random path and stuff? So what he had to do was to find something common between all these paths. So so it turns out that each point, like if you consider this, at this point, it has a certain kinetic energy and a certain potential energy. And at every point of its motion, it will have a certain kinetic energy and a certain potential energy, right? So he thought to himself, yeah, so then I can define maybe a quantity that changes over time and has the units of energy, and then maybe if I do something like that, I'll get it. So what he did is he defined like the principle of least action defines a quantity called action. In Lagrangian mechanics, is the time integral between of the Lagrangian with respect to time. Yeah. So what it does basically is it basically just like it integrates over all the energy at each point to give a certain value of action. So if you consider maybe this path, it'll have a certain energy, and then when you integrate it, you'll have an action. But if you consider some wildly different path like this huge thing, it'll have a completely different action for opposite of that path. So according to the principle, the object will always take that path which requires the least amount of action. So, so like it found like when the object takes this path, it actually has the least amount of action already. So the smallest deviation from it is probably what the what do you call object will take. That's why a pendulum just doesn't go like nuts and just goes randomly. So it just always takes its path because it's the path that requires the least amount of like energy, or it's the most efficient path to take. And then, yeah, so from the principle of least action, you can like derive the Euler-Lagrangian equation. This equation is just it's just too useful everywhere. Like this is actually one of the simplest form of the equation, but it's just beautiful. For a Lagrangian, L Q of t, Q dot of t, Q dot is just the first derivative of Q, and t, you can define this. So the partial derivative of the Lagrangian divided by the partial derivative of Q minus the time derivative of this will be equal to 0 according to Euler-Lagrangian equation. So here you can just consider Q as the axis or the coordinate. Example, this you can consider Q as theta, because that's like the main coordinate that's changing all the time. Okay. So like to understand this better, we can just consider this very simple example. So let's just consider a ball falling under gravity, just free falling. So then you know that the Lagrangian can be written as E minus V. So then the potential energy minus the kinetic energy, right? Kinetic energy minus the potential energy. So then you can write the Lagrangian as half mv square. So x dot is the position of the particle. So x dot is nothing but v. So half mv square minus mgx. So then, so we can just directly substitute this into the Euler-Lagrangian equations. I hope everyone like has a bit of math under their belt, just partial derivatives. So when you just partially derive this, you just get minus mg, because x dot doesn't is when you partially differentiate x, it's a 0. So you get mg minus mg. And the second term, when you do it, you get time derivative of mgx dot. So mgv. And dv by dt is nothing but acceleration. That's what mx double dot represents. So on simplifying, we just get the acceleration of the system in negative g. So what we just did was we found the kinetic energy, we found the potential energy of the system, then we partially derived it, and then what we found out was it has the acceleration of negative g. We did something that Newtonian mechanics could have just taken, like F equal to ma, and then we could have put minus mg equal to ma and a equal to minus g. We did something that Newtonian mechanics could have done in 2 lines. We just basically crushed a walnut with a whatever this thing is, instead of just using Newtonian mechanics like a sane person. But the thing is, Lagrangian mechanics has its own place. This was a very simple example. So that's why we don't use Lagrangian mechanics everywhere. We don't over constrain the system. We don't just simply do it. So we use Newtonian mechanics wherever it's really simple, like just friction, simple forces. But Lagrangian mechanics usually gives us an analytical view of the whole thing. And these are just some of the uses. This is literally what I could rip off Wikipedia, but then there are just way too many more. So I guess this is like a midpoint. Anyone has any questions they can ask?
Yeah, Abhishek,
Yeah.
when you said the charge conjugation symmetry is possible for gravity as well, like what does that mean? How can you explain,
So you mean?
for example, gravity?
Yeah. Okay. Yeah. So then, it doesn't matter, right? If you change the whole Earth was negative in charge and the sun was even negative in charge, it doesn't matter. Like gravity doesn't depend on the charge, right, of the object. So that's why I said like even gravity doesn't matter. It is obey.
Yeah, Abhishek.
Yeah.
The principle of least action basically implies that the object will take that path where the quantity t minus v will have its minima at that point, right?
Not exactly, like it'll take a path where the action is the minimum. It's this the
Like the
action.
integral LDT. Okay, got it. So the this action of a system should remain minimum at each point of time in that path compared to all the other paths that it can take, or we are talking about the aggregate, like the
Yeah,
total.
the whole path. We don't consider each point of a path. We just consider the whole path,
Okay,
and then we sum it up and we
sum
check.
it up. Okay,
Yeah.
got it.
Yeah, I didn't exactly understand what is the principle of least action exactly. Like, why do we use that to determine the
Okay.
path of an object?
Yeah, yeah. So have you heard of Fermat's theorem? The when light takes light will always take the path that requires the least amount of time.
Right. But
Yeah. So then it's like an extension of that. You can call this like an extension. So like light, when it reflects off a surface, it won't just randomly go somewhere. It'll take the path that requires the least amount of time. That's something like that's what Fermat's theorem states. So in Lagrangian mechanics, we just consider the whole path because we're just doing that because we're trying to explain what happens. So it's like it's a mathematical model actually.
all
So
right.
yeah, so basically the principle of least action just helps you determine, show where the body will go. It doesn't. It's I can't say it's absolute because there's always some exception or the other.
Is there an exception to this?
There might be. I'm not sure about it.
All right. All right. Thank you.
So before I get into the next stuff, I want to give a bit of history background. So Einstein, he just published his general relativity in 1915, and then it just went wild. Like people, like it was so ridiculous that no one could believe it at first. Like, so then it just answered so many questions, and then it actually had to, like, so many questions had to be answered about it. So then all mathematicians were like scrambling to make a mathematical model of GR. So then, but then there was one really troubling issue for every of the, whenever you come across it. So according to GR, space-time contains energy, and energy warps space-time. So according to it, space-time itself should warp space-time. That's ridiculous. We don't see the sun suddenly become some small thing and just run away from us. It doesn't happen like that. So this was a issue, like, and they didn't know how to do something with it. So two German mathematicians, David Hilbert and Felix Klein, they just, while attempted to solve this, they came across like a tautology. It's like basically when you know, have you ever solved some equation and then you just get like 0 equal to 0? That's what they got. It just didn't make any physical sense, or it didn't have any significance for them. So then the whole conservation of energy in general relativity was broken. It didn't work, and it would never be accepted if conservation of energy would not be valid. So, like, for the time being, this equation is basically an equation in general relativity. So for the time being, like, the thing they said was, like, on the right side we have like the energy that is which warps space time, but on the left side we have energy that is contained in space time, or one of the other. So that was like the momentarily experiment, explanation, and like they couldn't do much about it. Like, so they needed a mathematical model to fix this entire thing. So what these two mathematicians did, the Hilbert and Klein, so they invited a pretty young mathematician called Emmy Noether, like Noether. I'm going to call her Noether because I know there are a lot of pronunciations, so I call her Noether. So they invited her to solve this equation. Like, she was already pretty well established mathematician at the time, but then because of her gender, she was not very well received in many places. Like, she just got really bad offers at every university she went to. Like, no one would ever give her a professorship, even though her list of publications by this time would probably exceed like two, 3 pages. But no one really recognized her. Even at the conference with these two mathematicians, like, they had to sneak her in as an assistant. They found a loophole to get her in. That's the only way they could do it. So she gave like maybe like 4-5 months to physics, or even a year maximum. But the contribution she gave is like insane. Like, we still use it till this day. So she not only did she manage to solve the problem of conservation of energy in GR, but then, you know, like every mathematician, what they do, whenever you get any problem, they just do one thing. They generalize the hell out of it. They just take an equation, generalize it, and then they give it to us. So this is what, she is a mathematician. So she did that. So we come to Noether's theorem. According to it, for every differentiable symmetry that exists in a physical system, there will be a corresponding conservation law. This also works in the inverse way. For every conservation law that exists, there has to be a symmetry in the physical system. So in practice, in reality, every continuous symmetry has a corresponding conservation law. This is the core principle of Noether's theorem. Like, the original equation is very complicated, but then I thought I like try to give you a bit of like a small example of how this works. So, like, again, let's just consider a car going on a very, very flat road, like no bumps at all. So here, if I change the position of the car from one point to another, it doesn't matter. if I change, like, if it's starting or beginning, it doesn't matter. Like, it's okay. The position of the so basically the position of the car is irrelevant of for the physics. So then the position of the car is symmetric, like with the thus. So it has a translational symmetry. That's what it's called. So we can say that the potential of this car is constant because it's a very flat road. So mgx, it's just the same all throughout, right? So I'm just going to take it as negative v because I made an error. This is the correction I'm making. So the Lagrangian of the system is half mv square plus v. And from the Euler Lagrangian equation from before, we can find out what the system represents at this point of time. So, okay, if we solve this first integral, we get 0 because v is not dependent on x, and half mv square is not dependent on x. Okay, cool. And the second term, when we do it, we get d by dt half mv square plus v. So then you get d by dt half, like d by dt mv. So I think everyone knows that what the potential energy of a system is. Like, no, the momentum of a system is, it's m into v. So from this equation, we can determine that d by dt into p equal to 0. So that means that the momentum of the system is conserved. And the only thing we assumed was that system is symmetric with translation. So this is like a really simple example of how any symmetry determines a conserved quantity. Here, translation symmetry determines that momentum of a system is conserved. Similarly, what Newton did for her theorem, like to prove GR was not prove GR, to make maths consistent with GR. She made energy of a system has to be conserved since time is conserved. Because like you can really take, like, it's like this point just blew my mind. That's why I did the talk exactly. So it's like whenever you apply a force, it doesn't matter when you do it, it's going to be the same effect. That's basically time symmetry. And relating time and energy was one of the biggest things that it just revolutionized physics at that time. Like, not only did she prove that time was like energy was conserved only when it was time symmetric, but like she proved every, like, a number of them. This is the mathematical form of Newton's theorem. Actually, it's a bit complicated, but once you like get into it, it's pretty simple to understand. Here, n is a quantity which determines the number of symmetries in a system. And yeah, Q and L are the same. And TR and QR are generators. It's not okay. Generators are basically like just going to put very simply, it just generates a few numbers in a group. So according to this equation, delta T equal to summation of R, epsilon R and TR. Epsilon R is always going to be greater than 0, and R varies from 0 to N. This is not very important to this is really complicated to understand. Even I'm not qualified enough to like talk to you about this in more detail. But then for time invariance, you can consider, like, for time invariance, I just want to consider T. So delta Q doesn't matter to me. So we can just consider it 0. So QR is 0. And since time is invariant, so there's only one symmetry, which is time. So 1. And you can actually take any number for TR. There'll be always a corresponding epsilon R. So you can just consider T as 1. So once you do something like that, once you solve it more, you get that energy is conserved in a system. This is what she did. This is how they proved it for in conservation of energy. Okay, so then this is the list of transformations, and like this is basically the list of symmetries and the conservation laws. Like the original one I wanted to get was way too big; it couldn't fit in the page of the table. So this is like condensed form. So we can even say like because charge is conserved, like charge, like it's in electromagnetic theory, the because it's charge symmetric. It doesn't matter if it's positive or negative. Electromagnetism will be fine. So that's why charge is conserved in the universe. And yeah, there are many more examples like that. So this is just one of few of them at this point. And even rotational symmetry conserves what you call angular momentum basically. So I just wanted to briefly, like that's all about conservation laws for now. And I just wanted to briefly talk about supersymmetry. I'm pretty sure many like people have just heard supersymmetry being thrown around like as just pancakes. It doesn't matter. So what they did, the okay. So before you answer, this is a basic principle of supersymmetry. You like so every force, say electromagnetic force, gravitational force, so many nuclear weak forces, nuclear strong forces. They use a particle called bosons to like basically exchange information, and that's how a matter can transfer energy between them. For example, you can consider a electron and maybe an atom, just a hydrogen atom, simple one. The boson for electromagnetic forces is a photon. So that's the way electrons and protons can exchange energy. If an electron gains energy, it can gain through a photon, and it will increase its state from ground state to excited state. That's like an example of boson. And I'm pretty sure recently people have heard about, not recently, pretty long back also, people have heard about Higgs boson. So Higgs boson, like it basically gives mass, particles their mass, but we knew that much, we could get that, but then we didn't know how much it gave. Like there was no like theory that said, okay, this particle will get this much mass, or even even Higgs boson is pretty light, but when it's supposed to be really heavy according to like a previous standard model. So to explain all these inconsistencies, the principle of supersymmetry is actually used, according to which matter and forces are symmetric. So basically, if you take an equation and you interchange matter and force, you get this. You should get the same equation. That's what principle of supersymmetry is trying to say, and it's different from theories of supersymmetry. Theories that use this principle are called theories of supersymmetry, and none of them. It's very controversial right now. None of them have been proven and stuff. So this is like a brief touch on supersymmetry. Yeah, so we can make whatever mathematical model we want. Universe is always going to come and stab us in the back. Just hates us. So let's just consider like a small thing, like a really small example. So we know that I'm pretty sure everyone knows what this is. It's like the cosmic microwave background. It's basically the light that has been around since the beginning of the universe. So at the Big Bang, light was like just emitted at like a ridiculously high frequency, maybe gamma, or little maybe higher, or even visible frequency. You could like see, like before the universe, it just used to look white. That's how bright it was. But then when we look at this cosmic microwave background now, it's in the microwave spectrum, as it says, because the light has traveled since the beginning of the universe to us. And as the space expanded, the light also expanded along with it. So then the wavelength of the light increased, and it basically lost energy. It just lost energy. So where did this energy go? Well, the answer is nowhere. It just went. It just gone. Like from it just was there, and then 13.8 billion years later, it's gone. So So actually, the Lagrangian of all the energies in the universe can be approximated to the the energy in matter, and then the energy in the electromagnetic spectrum, and the energy in space-time. So this last term is really, really like just bad now. So then what it turns out, like we know that the universe is expanding, right? So it turns out that the time derivative of this energy in space time is greater than zero, which means the energy in space time is not the same. It keeps increasing yeah. So basically, what this says is that energy is not conserved. Law of conservation of energy is a lie. We've all been lied to. But then for our purposes, it like this L of space time is so small. It's so small. Like you just might as well consider it to be zero. The only time this will ever come into play is when you consider the moment, like if you consider it in the cosmological time scale, like 10 billion years, 20 billion years. That's the only time this term will ever come into play. But for our purposes, it's just might as well be, man. It's so small that energy, yeah, just use conservation of energy, it works. So I guess I just wanted to end with that note. I just wanted everyone to question the conservation of energy. There's actually, yeah, so, and I hope people learned something from this.
Yeah, Abhishek.
Yeah.
According to Newton's theorem, as you told, that systems involving symmetry will have one conservation law operating. But how does that solve? How does it solve that initial problem of energy bobbing space-time and space-time containing energy?
You mean
Like,
like this problem, right? Like this
yeah,
issue.
how does
So
that theorem solve this?
yeah, that's a bit complicated, really. But then this helps distinguish between the energy that is in space-time, but the energy like which is conserved due to a time symmetry really doesn't how do I put it? It doesn't solve it like exactly, but then it gives a basis for it. Like these two mathematicians, when they solved it, they got that zero equal to zero type of thing. But then when you use this kind of conservation of energy, the basically this notation, like when you use energy, she basically had to redefine the energy which was used in GR. You couldn't use the traditional half mv square and stuff. So she had to define, like, we got this term for energy, and using that, we could distinguish between the different kinds of energy in space-time and the one that actually warps space-time.
Oh,
Yeah, Abhishek, for the supersymmetry, you said that we have, the supposed idea was mass force symmetry. So how
Yeah,
exactly does
mass.
that work? Like,
Yeah, it's very complicated. I really, this is the principle basically. But then in theory, there's a very wide range of ways it's used. But this is just the principle. Proving it, like it requires really, I'm pretty sure it requires a bit of math, like a bit high-end math.
because what's the logic? Like, do you just let the spin? Like, if you for matter you have integral spin, for force you have fractional spin, right? So do you just change them or exchange them, or do you just what do you mean
Sorry.
by symmetry in that case?
Yeah. So symmetry in this case basically means, like, if I exchange matter and force. So suppose I have an equation, some random equation which has a force quantity and a matter quantity, and I interchange both of them. Suppose like f of xy equal to x square plus y square. So there's a x term and a y term. So that equation, if I exchange x and y to give f of y and x, you still get the same equation, right? In that sense, they try to use matter and force as the same thing. Like when I switch the terms, it should give the same equation or the same physical meaning.
So basically, the reason we have laws of conservation is because of existence of symmetry.
Yeah.
Wow. Okay. Awesome.
Krishna Joshi asks, does the Lagrangian of dark matter exist?
I guess not yet. See, this is the dark, not dark. See, this Lagrangian is the Hamiltonian energy of the entire thing. So you can maybe you can make an argument to say that the energy of dark matter energy is already in this energy. We know how much energy is there in the universe. We call it dark energy because we just can't see it anymore. That's it. You just don't know where it's coming.
So Abhishek, there's one more question in the chat box
Yeah.
from Nikhil Koneru. So he asked, could you again explain how that space-time warps space-time is explained?
Yeah, that's like there are many ways to different versions of the same story, man. But this is like a really basic thing. Like I can't explain more than that. But so in Einstein's relativity, you can say that energy is contained in space-time. Like space-time is not empty; it has something going on always. So then there's some intrinsic energy inside it, and space-time and energy is supposed to warp space-time. So something like I'm pretty sure everyone has seen that experiment where you take that really stretched out sheet and then you put gravity like there's some ball in between and just like that. That's like an analogy for space-time. So you can say that gravitational energy bends space-time around it. So the problem which they came across was something like this is a very it's like a very flashy way to say it, but this is not exactly what happens. But then it's if that would happen, why can't space-time just bend itself to give some random things? Why do it need another external energy to bend it? So that's what these terms a bit like. You can really explain it with that. Like in this is a tensor for energy, and you can consider this as a matrix, and only the what you call diagonal matrices uh, are contained in space-time. The rest of it bends space-time, which is in this part of the equation, which solves the entire thing. And to get this tensor, we use Noether's theorem and get it. That's how Newton actually solved space-time, that space-time issue.
So when you say Lagrangian of space-time, so does that mean kinetic energy of space-time minus potential energy of space-time? Like, I'm just trying to understand
No,
the
no.
physical.
No. Yeah, so that is for like the L equal to T minus V is only used for like non-relativistic purposes. But when you're talking about relativity, we use a different thing. But I told right, so space-time has some kind of energy. It's not always empty. There's always like some particle coming to its existence and then just disappearing on its own. The only way that's happening is if there is some energy in space-time, like even when you consider like just a box inside, you think there's nothing, but there's always like some molecules moving around, hitting here, there. So you can maybe consider that to be it's not exactly space-time energy, but then uh, the proper definition would be the underlying quantum fields. So that would give energy, space-time energy. And it turns out like there's more space-time being produced each time, and so there should be more quantum fields occurring. So there should be more energy. So it doesn't like stay constant with that.
I just wanted to add that not all Lagrangians are the same. And then there's a very famous, picture, which shows why physics is physicists are limited by math. It is the Lagrangian of the Standard model of the universe. Let me link a picture to it. So if you see, this is the whole thing is the Lagrangian of the Standard model and describes how particle physics works in itself. Thank you for attending our talk on symmetry by Abhishek. We hope all of you learned something. All right, guys. Thank you for attending.